Hello everyone. In this short video, I want to talk about something that is very important when you are doing numerical differentiation. And that is when you numerically calculate any derivative, the total error that you have, which is the difference between the approximation that you get and the actual value of the derivative, comes from two sources. One of them is the truncation error that we talked about in my previous videos, and the other one is roundoff error. So the truncation error comes from the fact that when you calculate the Taylor expansion for f of x plus h or minus h or plus 2h, when you basically look at these terms, you know Taylor series is an infinite series, but you cannot keep adding and subtracting terms forever. So at some point you say these many terms are enough. After that, I'm gonna ignore it, and that is when your approximation starts. And depending on how the remaining terms that you ignore, they are proportional to what power of the step size you come up with this term, right? So for instance, if you looked at my previous videos, you know if I use forward or backward difference, both of them, in them the order of error is proportional to the step size, linear. If I use a central difference, the error is proportional to h squared. And if I use the 4-point, or maybe in one of the videos I call it 5-point difference, which I use 4 points in it, is proportional to h to the 4. Okay, now we typically use h's that are less than 1, step sizes less than 1. So we expect that as we use more points to approximate the derivative and this power goes up, because the numbers less than 1, when you raise them to any power bigger than 1, they get smaller and smaller. So h is bigger than h squared and is bigger than h to the 4. You expect that when basically you go from forward to central and from central to 4-point method, first of all, the amount of this error goes down. The other thing is, because h itself is less than 1, if you make this h smaller, if you pick smaller step sizes, you expect this error term, which we call truncation error, to be smaller as well, right? So if I use 0.1 or 0.01, I expect that for 0.01 I should have a smaller truncation error. And it is, indeed, it is smaller, okay? But that is not the only source of error. And this topic just came up today in my numerical or advanced computation class. I showed the performance of these three methods, forward, central, and 4-point, and backward, for different step sizes. So I generated this plot for them. This is the absolute error. Here I had the function, so I had the exact value and I did the approximation. And here in this logarithmic plot, you can see that, first of all, for the same step size, let's say 10 to the negative 2, the error of the 4 or 5-point method is much smaller than the two other ones. So look, this is around 10 to the negative 10, this is around 10 to the negative 5, this is around 10 to the negative 3. So this is the more accurate method. And as I move from right to left and my step size gets from 0.1 to here 0.0001, my error should drop. And you see that these are downward curves and they are all dropping. Okay, they are decreasing functions. So everything looked fine except for one part, which is this portion here. If you look at this portion, this is very interesting. So here I'm going from a step size of 10 to the negative 3 to 10 to the negative 4, and I expect that my error keeps going down like this, but guess what? It didn't. It went up now. Basically, this one tells me that with the 5-point method, a step size of 10 to the negative 3 is working better than 10 to the negative 4 because the error of it is smaller. So it says, hey, after 10 to the negative 3, the more you make it smaller, you might not necessarily get any better results. For these two, it is still the case. Look, if I go from 10 to the negative 3 to the 4, they're still going down. So for forward, backward, or central, if I go further down, I get better results, but not for the 4 or 5 point method. My error gets a little bit worse. And one of my students asked, why does this thing happen? And the answer is this, as I said, that if the source of error was only truncation error, you are right. This should have gone just down like that. But the problem is we have another source of error, and that is this guy, roundoff error. Because our computers can only store numbers with so many decimals, with so much precision, that is when the roundoff error shows itself. And you might say, what does that mean? So let me explain that to you. So look at what you're doing in the numerator of this 4 or 5 point formula. Look what you're doing. So here I'm subtracting f at x plus h minus f at x minus h, or f at x minus 2h minus f at x plus 2h. So I'm subtracting function at so many steps ahead or before the current point. So I'm comparing these two together, and I'm comparing these two together. They're subtracting. But when this number is very small, let's say x, the point that I'm interested in, is 1, and let's say h is 10 to the negative 4. So what are these 2 points that I'm calculating? One is f at x minus 2h, so it is 0.9998, and this one is f at 1.0002. So you see, I'm subtracting f at 2 points that are very close to each other. Yes, they are extremely close to each other. And if, when I'm storing the values of f, I only store them with 2 or 3 decimals, these two numbers are going to be very close to each other. They might even cancel each other to a huge degree. And then I'm dividing that by the small number, which makes it very big, and then you're going to get more roundoff errors. So you see, cancellation of similar terms and dividing by small numbers, these are something that your computer cannot handle very well, okay, because it only has so many decimals. And for 10 to the negative 4, it might not be super bad, but imagine this 10 to the negative 4 was 10 to the negative 8. Now, what are you comparing? Now, one of your numbers is like this, and the other one is like this. Six, 7, 8, something like that. Do you see? Now look at these numbers. Now look how close they are. This one and this one, they are practically in the limit. When h is very small, these two numbers could be ideally close to 1. So both of them are like f at 1, and they literally cancel each other. So as h gets smaller, the truncation error for the Taylor series will go down because you are ignoring fewer terms. But the roundoff error can go up because now you get more similar terms that can cancel each other, and you're dividing by extremely small numbers. So as h goes up, the total error, which is sum of these two, might go down, might go up, depending on which one of these two is dominant. Now here in this other plot, which I'm going to run the code for it and show you, if you look here in this other plot, here I have again the forward method, the central method, and the 4-point method for different h's. And again, as I go from right to left, you see h goes from almost 1 to 10 to the negative 16, which is the limit of MATLAB. Okay? And here I have 3 plots for you. The red, the blue, and the green that are dashed lines, these are truncation errors only, which are proportional to the h squared, and h to the 4. You clearly can see that these curves keeps going down, because when you go this way, h is going down, so the truncation error also goes down. But the total error, which is sum of the roundoff and the truncation error, are the solid curves. Look what happens to the solid curves. For the red curve, which is the forward, it comes down to almost about this point, which is about 10 to the negative 8, and then now it keeps going up. So until 10 to the negative 8, a step size that small, you still can reduce the error, and you can do great. But after that, you get this what we call U shape, and you keep going up. So the truncation on this side, the roundoff error, as I said in the topic, this is bigger than the truncation error. The roundoff error will dominate. On this side, on the other hand, the truncation error is dominant. So once you pass this point, which is the optimum point, you make it any further smaller, you are not going to get better results, you're going to get worse results. Look at this one here. The blue one, which is the central, it goes down to about this point, which is about 10 to the negative 5. You are doing great, but after that, look, it keeps going up. And the interesting one is the 4 point. If you look at the 4 point, there is barely any U point. I mean, there is U, but it's very subtle. So mostly I can say for the 4 point, these two will kind of cancel each other to a huge extent. And their effect is not really super clean. So each method of differencing, right, forward, central, backward, 4 point, any, you have to find an optimum H value for it. And the answer is typically this: the more points you use, these two would come to equal magnitudes much sooner. You don't even need to go further down in the H to get these two to be of equal magnitudes. They can start literally close to each other to begin with. But the rougher method, the method with lower accuracy that you use, you see that it takes quite a bit of small h for the error to start going up. Yes, so more accurate methods, their U point is further to the right. Less accurate methods, their U point is further to the left. In other words, they need smaller step sizes. The forward or the central one, the backward, they need smaller H's to get the best results. This one works with a little bit bigger H to get the best result. This probably even bigger. Okay, so there is always some optimal H, and that does depend on the method that you use for finite differencing. And this is that code, by the way. So let me show you the code. So this is the code. This is that this is the one that generated the question for my students, right? You can see it goes down, then it goes up. And this is that code that shows the behavior of these. Okay? So you can see the 3 methods and their truncation error and the total error for each one of them. So hopefully this video was useful to you, and you learned that there is always an optimal H that you need for each method, and the total error comes from truncation error plus roundoff error. Thank you so much for your attention. I'll see you in the next video, and I will share this code under video description so you can download it and take a look at it. Thank you.